So today we're going to talk about hazards. So hazard is a situation when we cannot execute two instructions back to back. So that's called hazard. So if you remember, in ideal pipeline, every clock cycle, new instruction comes in, and old instruction goes out, right? It's like instruction flows through the pipeline smoothly. That's kind of ideal pipeline. But in reality, there may be some situation that we cannot really execute two instructions back to back. Okay, so in the big picture, let me give you a big picture first. So if you remember this classification, let's say there's hazard, and that there are three causes for hazard. The first one was structural hazard. Second one is data hazard. And third one is control hazard. Okay? So what are the solutions for this hazard? For structural hazard, what will be the solution? Structural hazard happens when two instructions in different stages try to access the same resource, right? And perhaps the only way to resolve this structural hazard is to replicate the resource, right? Now, for example, we have like a separate instruction memory and data memory, so that the instruction in mem stage and instruction in fetch stage, they can actually access the memory at the same time. In that way, we can actually resolve this like a structural hazard. So like to resolve this structural hazard, the solution is resource replication. Is having like more resource, right? And the second like hazard is like a data hazard, and there are three different ways to resolve this hazard. The first one is placing knobs. Placing knobs in your program, right? So if you actually have two instructions that are they may have like producer and consumer relationship, we can actually place like a bunch of knobs to set them apart. Then this like hazard goes away, right? So that's actually what I did like last time. So if you have like one instruction that produced the data, and second instruction actually used the data, then actually we put like a bunch of knobs in between, so that actually this value is written back to the register file before actually we read it, right? That's what it did. So explicitly placing knobs. The second solution is called like a stalling. The idea is basically the same. We want to set this like two instructions apart, but in this case, this placing knobs is done in hardware implicitly instead of like being done explicitly by software. So there's a second solution, stalling, and there's another solution which is called like forwarding. So these are basically solutions for resolving data hazard. Okay. Finally, to resolve this control like a hazard, perhaps the most popular solution is branch prediction. Because the control hazard happens because of conditional branch, right? If you have a conditional branch, you cannot really tell what will be the next like PC until you actually evaluate the condition, right? So there must be some like empty slots that we cannot really tell where the instruction come from. So that's basically called like a control hazard. So the solution for control hazard is branch prediction. Okay. So today what we're going to cover is these three. Okay, because we already covered these two in the previous lecture, so so today's topic is these two, and also I'm going to also cover a little bit more about this branch prediction in the next lecture. Okay, so that's a plan. That's a big picture. So, as I said, data hazard happens when instruction having register R as source follows shortly after instruction having the same register R as destination, right? In other words, if two instructions actually, access the same register, one is producer, one is consumer, they are placed in back-to-back, then that actually causes data hazard. And it's very common. I mean, it's a very common situation. So, and we don't want to slow down the pipeline because of this hazard. And second condition is a control hazard. It's actually caused by mispredicted control branch, right? So in our baseline design, we assume our design actually predicts all branches as being taken. That's kind of a prediction. Whenever we hit upon branch, like a JNE or JGE or something like a branch instruction, we assume this branch will be taken. Taken means the condition will be satisfied. So we actually fetch the next instruction from the target address, jump target address, right? But of course, this is just prediction, so we may be wrong, right? In like an E stage, we evaluate the condition, finally evaluate the condition, and we find that, oh, this prediction was wrong, right? Then in that case, we actually have to basically flush the pipeline because we actually fetch the instruction from wrong PC. So we actually have to flush the pipeline and then start fetching again from the correct a PC. That's what's happening. And also there's another control hazard caused by RET, like a return instruction. So think about return instruction. So return instruction, you actually have to access the stack, right? Because if you actually hit upon like a return instruction, you have to pop those return address from the stack, and then you actually have to jump to that address, right? That's what this return instruction does. In other words, you cannot really get this like a return address until you access the memory, right? Until like M stage. So there's some slots, for which we don't know how to fill those slots, right? So in mispredicted branch condition, we execute like a 2 extra instruction, and in the night pipeline execute like a 3 extra instructions for like a return instruction. Okay. So also we want to make sure it really works. That's what we want to talk about, in this lecture. So if you review this like a basic like a five-stage pipeline stages, we actually this one is like instruction flows in this direction from bottom to top, and every instruction actually goes through five different stages from fetch, decode, execute, memory, and write back. Right? That's our like basic like a pipeline we covered like last week. And this one is more detailed view of pipeline hardware. Let's say this hardware is pipe instead of SEQ. So we actually place a bunch of like 5 different pipeline register labeled capital F, capital D, capital E, capital M, capital W. So we have 5 different pipeline registers, which actually sets the boundary between stages. Okay, and those registers hold intermediate values from instruction execution, right? So if you actually finish fetch stage, then actually your like computation result will be stored in the next pipeline register, which is D. And once you finish executing like a D stage, the result of computation will be stored in the next pipeline register, which is F, which is E, and so on, right? And values actually pass from one stage to next, from bottom to top. And regardless of whether you're going to use specific stage or not, you actually still have to go through 5 different stages anyway, right? So there's no bypassing of the stage, because that's how this pipeline works, right? So let's say, in this case, let's think about jump instruction, like JNE like a loop, something like this instruction. Then even this instruction does not really require access to register file, right? It doesn't have any like a source operand or any destination like register and so on, right? So it doesn't need to access this like a D stage, but still, this instruction still needs to go through these 5 different stages in sequence, even though it doesn't really need to do, because always instructions will go back to back, so you have to always follow the previous instruction in the pipeline, right? So that's what it means by we cannot jump past stages, even if one instruction may not use like all these stages. Still, they actually have to go through 5 different stages. So think about, this, like, let's start with data dependencies. Think about this scenario. I think we covered this one last time. But, here's a situation of, like, data hazard. Here, this is the producer. We actually put constant 3 to RAX register. And this value will be used by this, like, later add instruction, this, right? So let's assume, this instruction is these two instructions actually have 2 knobs in between. Then what happens is, here, let's think about this cycle 6. In cycle 6, this, like, the move instruction actually move instruction is in the write back stage here, and this add instruction is in this stage. And the add instruction tries to read this, like, a register value of RAX, right? But when this value gets actually updated, RAX register, because the register file is sequential logic, this value is actually updated at this point, right? So the register value of RAX will be updated at the rising edge of the next rising edge of the clock, which is the end of, like, cycle 6, right? But the problem is this add instruction tries to read the value in the beginning of, like, a cycle 6. In other words, the second instruction tries to read it before the value is written back to the register file. So this is problematic, right? So our solution in the previous lecture was we actually place one more knob here. Then the problem goes away, right? Because now, this, by the time when the second instruction reads this, like, RAX register, the correct value will be written back in the register file already, right? This is what it solved the problem. And alternatively, what happens if we actually have, like, no knobs between the two? So if you have no knobs, there are 2 data hazard. The first one is caused by this RAX register from here to here. And second one is caused by this RDX register from here to here, like this. Okay? So in cycle 4, for example, so M register, the first move instruction, this one, the first move instruction is passing through M stage in cycle 4, and second move instruction is passing through the E stage in cycle 4, right? And in both registers are not written. Neither of the register is written back to the register file. They actually, their value is available in the pipeline, but still, it needs to be written back first before the second instruction, the add instruction, reads it, right? So if you actually read it, I mean, in this cycle, the add instruction tries to read the register value, RDX and RAX, and both, it actually reads, like, an old value of the register, those 2 registers. So this is problematic. Okay? So the first solution we actually have, the first hardware solution is first solution is like stalling, how stall the pipeline. So we can actually solve the problem in this way. So if you actually have, like, this instruction sequence, this one needs to be updated, and this one needs to be read. So if the instruction follows too closely after one that writes the register, and we actually need to slow down the second instruction. So how we can slow it down? So let's think about cycle 6 here. Cycle 6. In cycle 6, we actually have 5 different stages: write back, memory, execute, decode, and fetch. We actually have 5 stages, right? 5 stages like this, right? So we actually have what instructions are there. So in cycle 6, the IR move Q is here. And in M stage, there's NOP. And in E stage, there's another NOP. And in D stage, we have add Q. In F stage, we actually have halt. So this is a snapshot of the pipeline in cycle 6. So in cycle 6, we have, this one is in W stage, this one is in D stage, this one is in F stage, right? So what So if you actually stall the pipeline, then stalling means the pipeline dynamically insert a NOP, no operation, into the pipeline, between the two instructions. So in other words, so we hold, this like a second instruction in decode stage, and the rest of the pipeline actually make a progress forward. So in cycle 7, in the next cycle, if your stall is applied, let's say we actually apply stall here. So if we apply stall, these two instructions actually stays there. These two instructions stay there, and then the remaining 3 instructions on the front end, they actually move forward. And we insert a no operation between the two. Okay? So these two actually stalls, and these two actually stays there. At Q is still there, halt is still there. But the other 3, these remaining 3 instructions actually make progress to the next stage. So this one actually graduates, this one actually goes away, and NOP moves to, this one moves to W stage, and this one moves to M stage. And what are you going to do to this box, this place? So now we actually have one empty slot, right? Because now these instructions move forward, and these 2 instructions actually stays there, and now we actually have one empty slot. Oh, bless you. So what are you going to do with this box? We have to place NOP here, right? We play the hardware, the pipeline itself actually plays no operation here, right? Then the program goes away, right? So at the end of cycle 6, this move instruction will write the value to the register file, and then in the next cycle, this add instruction will retry, to read the register file and read the correct value, right? So that's the idea of stalling. So the point is, even though we don't explicitly put a NOPs between the 2 instructions, it automatically, the hardware in the pipeline automatically insert, bubbles. I mean, NOPs. Bubbles or NOPs, the same thing in its context. Insert this NOPs automatically if this a stall condition is detected. Okay, that's what this stall does. By the way. Too hot. Okay. Understand what this stalling does? I mean, what is happening here? 네. 네. 맞아요. 다음 슬라이드에. Thank you for doing some preview of what I'm going to cover. So it's a very good question. So how we detect the condition? The first question is how do we know whether there's a stall condition, there's a stall condition is there between these between pair of instruction or not? So we actually have to do the following. So stall happens. We actually need to compare the register, like a source operand in the D stage, like decode stage, with the destination register of any of the later stages. If they match, then there's a stall. Then we need to stall, right? Because let's think of the source register first. So source registers. So we actually have 2 source registers in decode stage. Let's say because in decode stage we read the register, right? So that's a place we actually take the source register ID. So there are 2 register ID, source A and source B, of the current instruction in the decode stage. That's a source. In the destination register, there are 2 destinations, either DST-E or DST-M. Because the value could be generated from either E stage, like execute stage, or memory stage. So depending on where the value comes from, we label it as dest-E or dest-M, right? So 2 destination registers. So in instructions in execute, memory, or write back stages, and we compare every pair of this a source and destination. And then if there's any match, then actually we need to stall the instruction. Okay? So if there's like match, that means the instruction that actually generates the read is currently in the pipeline. So we actually have to wait until this this instruction actually retires from the pipeline, and then only after that we can actually read the correct value from the register file. Okay, yes, for you. And of course, there are some special cases like don't stall for register ID 15. So register ID 15 means it's no register, right? So some instructions do not writes to the register at all. In that case, we have like we set the destination field to F. F is basically no register. So we did that like register ID 15 indicates the absence of register operand or failed conditional remove, right? So if like destination register ID is 15, then we don't have to worry about it because it's like no register, right? So here, let's see how this like a store condition works. So here, again the same example, move followed by like add. So we actually have IDX register written back here, and IDX register to be read here. So here's dependencies. Here's dependency between the two instructions. So in cycle 6, this instruction is in write back stage, and this instruction is in like a decode stage, right? So in the write back stage, the DSTE, this is the ID of destination register, and this one is IDs of source registers. Right? So we basically compare every pair of destination register with every pair of destination register and source register. So we compare this one with this one, and this one, and this one. And we actually found the match, right? Because this one, the instruction in W stage tries to write to the IDX register. And at the same time, the instruction in D stage tries to read it at the same time, right? So in this case, this one actually has to stall. This instruction must stall for one cycle so that this value will be written back to the register file first, and then in the next cycle, you can actually read the correct value of 3. Okay, this is how we detect this stall. And if we have like these two instructions back to back, let's say there's no bubble at all. If there's no bubble, then in like cycle 4, this instruction is in E stage, and this instruction in D, and the destination register for the instruction in E stage is RAX, because we actually have to do like this pairwise comparison for all possible pairs of destination register and source register, and actually we find the match here. These two. Then we need to stall. Okay, and stall happens. This like instruction in D stage actually has to stay there, and then all the remaining instructions actually make a forward progress, right? So in the following cycle, this instruction actually moves to M stage. In the meantime, this one is still staying in D stage, and in the next cycle, again, we find another stall condition with this and this one. So in other words, the instruction in M stage tries to write to RAX register, and the instruction in D stage tries to read it from the same register. So we actually have to store again. So if you store again, this instruction will stay in D stage again, and this will make a progress to W stage. And again, there's one more time this store condition fires, and you actually store one more time. And eventually, this one actually moves out of the pipeline, and now this store condition has resolved, and then now this one can read the correct value of register and move forward progress in the next cycle. So that's basically stalling. And all of these like bubbles, bubble is like an up, this knob. All of these bubbles are inserted automatically by the pipeline hardware. So second question is, what happens when stall happens? Okay, so we actually talk about stall condition. I mean, how we can detect a stall condition. And we need to take some action, right, once stall has been detected. And what needs to be done if you have a stall? So if stall happens, the stalling instruction, in this case, this add instruction is a stalling instruction, right? The stalling instruction is held back in decode stage. Okay, so it stays there. It basically retries. It retries until this like a stall condition is resolved. And the following instruction stays in the fetch stage because if the one like earlier instruction cannot make a progress, then the later instruction has to stay there too because it's actually stuck, right? It's actually blocked by the earlier instruction. So generally speaking, let's say we have 5 different instructions. Looks like this. Let's say this one is W, M, E, D, F. And it's instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. Let's say there are 5 instructions in the pipeline. If stall happens, this one is cycle 1, cycle I. In the next cycle, if a stall happens, in the next cycle, the instruction will look like these 2 instructions will look basically stuck there. I mean, I2 is still there, I1 is still there, basically retrying the same thing. But these 3 instructions make a progress, so it'll look like I4 will go here, I3 will make a progress too. And we insert like a knob here, no operation, like this. That's what needs to be done whenever you see a stall condition here. Okay, so bubbles injected into execute stage. This is the bubble. So bubble is injected in the execute stage, it's like dynamically generated knobs. So in the previous lecture, we actually placed this like a knobs in your code, right? Explicitly, you actually inserted this code, but it's more like it does the same thing, but it's actually dynamically generated by the hardware instead of like in your source code, in your like machine code. And this like a knob will actually move through the stages. Okay, this actually shows animation. So if you actually have this code in cycle 4, we actually have these 4 instructions back to back nicely up to like a cycle 4. But now we find there's like a stall condition, like this one versus this one, and this one versus this one, like this, right? In cycle 4, so what happens in cycle 5 is there's these 2 make a forward progress, but there's bubble inserted in EX stage, right? Because the hazard condition. And in cycle 5, we actually have one more, actually 2 more hazard conditions still there. I mean, this one and this one still cause a hazard, data hazard. So we actually need to stall one more cycle. In cycle 6, it will look like this. In cycle 7, it will look like this. And even finally, now we can make a progress, right? Because all these values we need are correctly returned back to the register file. So this instruction can now make a progress to the next stage, like this. That's what's actually happening, right? That's kind of animation showing what's happening when you actually have a stall. Then the next question is how we can implement stall. So now we move on to the implementation side. Hopefully now you understand when we can, what condition, what is the condition that actually generates a stall, and what needs to be done. And the next question is how we can implement it, right? So in this case, so we need to actually modify the pipeline controls here, like a pipeline control logic. So pipeline control logic is a combinational logic that detects all stall conditions. Okay, so there are multiple unit. There are like a bunch of like ifs, right? If one of these conditions is satisfied, then we actually have a stall, right? Either like DESTE and source A matches, or DESTE and source B matches in E stage or M stage or W stage. Any of these condition matches, we need to store the pipeline, and that's actually done by this pipeline control logic. And it actually generates a mode signal for how pipeline register should be updated. Because in order to implement stall, we need to control this like a pipeline register, right? So now we actually modify the control register, pipeline register in the following. So now there are 3 different ways of operation for pipeline register. So in normal operation, this is kind of normal operation. Now we actually introduce 2 more control signal, like a store and bubble, right? There are 2 more control signal bubble. If both are 0, then it's like a normal like a pipeline register. Every cycle it gets updated. So in this case, in normal operation mode, at the rising edge of the clock, the value, if the input value is y, this value becomes the new value of the register. So it gets updated normally, like a normal like pipeline register. And what if this like a store input is 1? That means we need to actually store the instruction. That means we don't update the instruction, right? Because we need to store. So if the store signal becomes 1, then at the next rising edge of the clock, the value is still x, right? So it's because in the previous case, whenever store happens, the instruction in decode stage and fetch stage needs to be, they need to stay there, right? In that case, we actually set the input to this like a register, pipeline register to 1, store input to 1. Then we actually keep the original value so that these instructions can stay like 1 more cycle there. And sometimes also we need to insert. Sometimes we need to insert a bubble into the pipeline register. So if you actually set this control value to 1, then at the next rising edge of the clock, the value will become null. Regardless of the input value, the value will become null, right? So in the previous like a stall like example, this one will apply to F and D stage, like a pipeline register, and this one will be applied to E register, right? Because when stall happens, we need to basically stall these 2 instructions, like a E stage and F stage needs to be stalled, and we have to insert into new bubble into the E stage. So this one is like E register, and the other 2 like M and W will be like this. Will like work normally, so that actually it gets updated in the next cycle. Questions? Any questions about this like forwarding and stalling? 뭐 어렵지 않죠? Okay. And in homework number 3, we ask you to optimize the pipeline and software together, right? So to actually reduce the number of cycles, right? And if you really want to get like a high performance like pipeline, you have to understand forwarding. Okay. So the point of forwarding is, can we actually eliminate bubbles? That's the question. So in like a stalling, we actually still have to insert like a bubble. That's kind of waste, right? We actually waste these slots for instruction execution. So the question is, can we eliminate those bubbles? The answer is yes, if we apply forwarding. So let's say how this forwarding is to solve the problem. So in the naive pipeline, I mean the pipeline we have covered so far, the naive pipeline, the register is not written back until completion of the write back stage, right? So any instruction needs to go to the like a W stage to update the register, right? And the source operands are read from the register file in decode stage. It's fixed, right? We can really change it. So if you want to read the correct value, then that value needs to be available in the beginning of the decode stage. That's kind of constraint we actually had. But can you actually overcome this constraint? The answer is yes, because actually the value to be written to the register is actually generated much earlier, right? Let's think about this, the same example, like this code. So so far we actually, this instruction, like this add instruction, has been waiting until the value is written back to the register file. But the question is, when this value of RAX register is actually available in the pipeline. When this value of 3, I mean, the 3 is the value, right? 3 is the value we need. When this value is available. 언제 available 하게 되죠? Actually, as early as like D stage, right? Because once you read the instruction, now you actually extract this val C from your instruction, right? Then this val C becomes available in D stage. You already, number 3 is already available, already in the pipeline, right? The point of this forwarding is, instead of waiting until this value is written back to the register file, why don't we just, forward this value directly to the input of the next instruction, without going through this register file? That's the idea. So the value to be written to the register file is generated much earlier in like execute or memory stage. So the trick is, pass the value directly from generating instruction to the decode stage, and make the value available by the end of decode stage. That's the idea. So we can we forward the value from execute stage to decode stage, or mem stage to decode stage, and so on. That's what we are doing here. So let's think about this example again, the same example. Let's think about this move add instruction. So currently, this IR move Q, this instruction is in write back stage in cycle 6, and the destination value is in W pipeline register, right? Because if you in cycle 6 in write back stage, this value 3 is available in like W underscore val E field in the register, like a pipeline register W. The value is already there. So what we do here is, instead of like waiting for this value to be written back to the register file, we simply just forward the value to the D stage directly. Just push the value into the D stage, instead of waiting for the value to be written back to the register file. So we forward this value directly forward this value into the decode stage like this. So in this way, we can actually save, like, we don't have to stall in this case. So in order to like support like a stall, support like bypassing, support like forwarding, we actually need to have like a bypass path. So we need to modify this, like, we need to modify this pipeline like a path, so that now we can directly forward the value from W stage to D stage, or M stage to D stage, M stage to D stage, and E stage to D stage, and so on. So now we actually have feedback path from like a later stage to earlier stage, so that if any of these like a later instruction actually holds the value is needed by this like a D stage instruction, then you can directly forward the value from later stage to D stage. That's the point of forwarding. So in decode stage, this forwarding logic, here's like a forwarding logic, like this box. So this box selects val A and val B, because in decode stage we actually generate two values, val A and val B, right? But by default, this val A and val B are read from the register file. So far, this is what it did, right? But we actually create one more like path from like a later stage of the pipeline into this like a val A and val B. So we actually, this logic actually selects the correct value. So So normally this value is actually taken from the register file, but forwarding, if forwarding is activated, then we can get val A or val B from the later pipeline stage, directly from the pipeline, from the pipeline register. And forwarding sources, where the values can come from. So in execute stage, maybe val E. In memory stage, val E and val M. In write-back stage, val E and val M. So there are 5 different sources that value can come from. So in this like a forwarding logic is nothing but a big MUX, multiplexer. So now we actually have, let's say we have val A here. So val A is selected from one of the 6 sources. One will be like from like a register file. Maybe value may come from register file, or it can come from one of these 5. Let's say this is 1, 2, 3, 4, 5. Then maybe there are like 5 different sources. 1, 2, 3, 4, 5. So now we actually have 6 different sources from which the value can come from. And this forwarding logic actually selects one of the 6, depending on the condition. Let's say if there's a match between the destination register and source register, in decode stage, we directly, forward the value from that stage to decode and so on. That's what this like a forwarding logic does. Okay. So here is a data forwarding example 2. Let's think about how we can data forwarding can solve the problem without paying the cost of stalls. So here, now we have 4 instructions: move, add, halt. So they are currently in M stage, E stage, D stage, and F stage like this. So we need to actually forward the value. Both register value needs to be forwarded from the later stage, right? Because there's dependency between this instruction and this instruction by using with like this register, and also there's another dependence between these 2, right? So let's think about the register RDX first. So first of all, there's a register RDX. So in M stage, M dest E is RDX, M val E is 10. That means, for this instruction, this instruction will update the value of RDX with the value of 10, right? But it's not written back yet, but that's what's going to happen in write-back stage. And in E stage, DSTE is RAX register, and val E is like a 3. So this instruction will update the value of RAX with 3, value of 3, right? It will happen in the write-back stage. But still, but the value is already available, but write-back will be delayed until the write-back stage, right? So once you actually see this, like in this situation happens, so the value of RDX is generated by ALU during the previous cycle when this instruction was in E stage. And we actually forward this value as val A because these 2 matches. So we need to this stage as val A. Thing happens for RAX. For in case of RAX, this one actually matches. We forward this value of 3 into the D stage as val B because this destination actually matches with this thing, right? So in this example, we actually forward these 2 values from EX stage, E stage, and MEM stage to like D stage. So about this case, so let's say there are multiple matches. And the question is how we can make priority. Which one actually has higher priority? So in this case, let's think about, all of these instructions actually rise to RAX register. There are 3 producers, right? And 3 producers and 1 consumer here. So there's dependence between these 2, like this and like this, right? Then this is like a 4 like consumer instruction, like RR move instruction. What is the correct value of RAX? 1, 2, or 3? 3, right? 그러니까 1, 2, 3 중에 여기서 얻어와야 되는 값은 3이죠. 3. Why? 마지막 업데이트니까 he is the last writer. I mean, their instruction like the third move instruction is the last writer to the register, right? And the later instruction always has to always read from this like most like from the last writer, the value of the last writer, right? So this value like 3 needs to be forwarded. But in our forwarding logic, we basically detect all these matching pairs, right? So we actually have 3 matching pairs. In the write back stage, this one actually this one is got WDST. This is the RAX. And this one is like MDSTE. This one is also like RAX. This one is like EDSTE. It's also RAX. All of these 3 actually matches to the source register of, like source A. Then which one actually has must have like a higher priority in this case? E, right? This one. This one actually has a higher priority. So if we actually have like a multiple like matches for these forwarding choices, then we actually have to use the value from the earliest pipeline stages. I mean, most recent value. So E actually has a higher priority than M, and M actually has higher priority than W if there are like multiple matches. So, 네. 좋은 질문인데요. 사실은 실행 안 해도 되죠. 이 경우라면. 이 명령어를 들어. 왜냐면 그 1, 2번 두 번의 인스트럭션은 프로듀스만 하지 걔 컨수머 하는 애가 없잖아요. 근데 그렇게 하지는 않아요. 그렇게 하지는 않는데 컴파일러가 똑똑하면은 근데 코드를 그렇게 만들 수도 있어요. 그러니까 만약에 컴파일러가 똑똑하면은 저런 경우라면 어차피 RAX 1, 2 두 번째 그 첫 두 무브 인스트럭션은 실제로 프로듀스만 하지 값을 쓰는 애가 없기 때문에 저는 불필요한 명령어라고 생각하고 그거를 없애버릴 수도 있어요. 저런 거를 데드 코드 일리미네이션이라고 하거든요. 데드 코드 일리미네이션이라고 부르는데 컴파일러에서는 상당히 중요한 옵티마이제이션이고 실제로 컴파일러가 코드를 저렇게 만들진 않아요. 왜냐하면 저런 경우는 라스트 라이트만 남기는 게 맞거든요. 그래서 코드를 저렇게 만들진 않는데 하드웨어는 그냥 동적으로 자기가 무슨 명령어를 노브로 바꾸거나 이런 건 없고요. 그냥 일단 컴파일러가 만들어준 코드는 그냥 페이스풀하게 다 실행을 해서 그러니까 결론적으로 얘기하면은 하드웨어는 그냥 저거를 그냥 순서적으로 실행을 하는데 컴파일러가 저런 코드 자체를 만들지 않아요. 왜냐하면은 저거는 있는 2개의 그 명령어가 쓸데없는 명령어로 생각하니까 데드 코드 일리미네이션 하면 다 그러니까 데드 코드 일리미네이션이 되게 간단한데 맨 마지막 컨슈머로부터 백트래킹을 해요. 컨슈머로부터 걔 프로듀서가 누군가, 걔 프로듀서가 이게 데이터 플로우 어널리시스라고 그러는데 그걸 쭉 해가지고 그 데이터 플로우 어널리시스 그래프에 잡히지 않는 애들은 다 그냥 필요 없는 코드라고 생각하고 날려버리는 거예요. 이제 그런 것들을 하는데 하여튼 이런 코드는 컴파일러가 만들지 않죠. 그렇지만 이건 그냥 이그젠플로 만든 코드니까 이런 경우가 만약에 있다면 실제로는 그냥 그렇다고 이제 실행을 안 하지는 않아요. 실행은 다 하는데 이제 데드 코드 그러니까 뭐 별 의미는 없는 명령어가 되는 거죠. Any other questions? 네, what? Yeah. Can you say again? What's up? Oh. So for example, what if for example, like what if this one's instead of like having like this move instruction, what if this one is add, for example, something like that? That's what you're asking. Shift or something, some other operation. The mechanism is exactly the same because if you have like an add or shift, then still you generate the value in execute stage, right? And also the destination register is held in DST E field. So if you actually execute, for example, let's take concrete example. Let's say in this case, add rdx, rax, followed by rr move rcx, for example. This is kind of, maybe this is example you mentioned. So maybe there's dependence between the two instructions via this RAX register like this, right? So in this case, let's say this one is in the E stage and this one is in D stage, right? Then we know that, oh, this destination for this instruction E, this one is RAX, right? Because we know that by decoding the instruction, we know that this add instruction will write the result back to the RAX register. So this information is encoded in this register, this pipeline register. So in this case, in D stage, we know that D SRC A is RAX. So we know that, oh, there's match between the two. So the point is, regardless of whether this value is like an immediate value or it's a result of like an ALU computation, still we actually use the same mechanism because we know that this value, this register actually is stored. Register ID is stored in the same field, and the value is also stored in the same field because this value will be eventually generated in E val E. So the result will be stored in like this field, like E val E, and regardless of whether this value is actually coming from this like immediate value or addition or shift, eventually this value will be stored here. I mean this one here. In this case, we actually forward the value from, let's say, the producer is in E stage and consumer is in D stage, and the value actually forwarded from the output of the ALU to the input of the next pipeline stage, like this. This is the forwarding path. So, let's say add is computed here and move is here, and there's dependence between the two, and add will become the result of add will be computed. And then it's actually forwarded in the same cycle. It will be forwarded into the input of the pipeline stage. So that value will become like a new val A or val B for when this actually move to E stage. Okay, did that answer your question? Oh. We will get there. Okay, don't go too fast. I mean, yeah, that's like a special case called the load user hazard. I'm gonna get to there. Okay, so all right. Actually, that's actually and it's like one student to correctly understand so far. What we covered so far. So here to implement forwarding. We need like additional feedback paths from E stage, M stage, and W stage into the decode stage, right? Because value can be forwarded from E stage or like M stage or W stage. There are 3 different stages that can produce the value, and we also produce a logic block that actually selects from multiple sources for val A and val B in decode stage. As I said, there are 2 like a forwarding logic, one for each of these like a val A and val B. So logic actually selects the one of the 6 values for val A, and this val B. This logic actually selects one of the 6 candidate values for val B. So if you actually use like HCL, the hardware control language, it will look like that. Look like this. This control logic, this box, will look like this. The val A is determined by the following rule. So let's say if the I code is call or branch, then the val A is directly taken from this like constant field, right? Because call and jump do not really need any like a register, source. Of course, call instruction needs to access this stack pointer, but otherwise, you simply, we can actually put this value as val p. So originally we only had these two. In our original pipeline, we only had like these two, this one and this one. If you recall, like in your like a sequential SEQ implementation, the val a is either val p or val a, depending on what the instruction is. But now we actually add this like a 5 new. This is new forwarding path. You actually add like a new forwarding path. So if the value destination register E in E stage matches with the source source register in D stage, if they match, then we actually get value from E stage, like a val E. And if it doesn't, now we actually compare the destination register in like M stage with the source register in D stage. If they match, we get value from this val M. And if it matches like with the dest E, then actually we get the value from val E in M stage. And if it doesn't, then actually we actually compare the value in the write back stage. Compare the register ID, like a destination register of the write back stage with the source register in decode stage. If they match, we actually directly get value from this forwarding path. Otherwise, we simply read from the register file. That's kind of the least, the lowest priority. So here is now we come to your question. So load use dependencies. So what happens if one of the producer instruction is load instruction? What happens? So here is a situation, like a somewhat problematic. So here, let's think of these two instructions, mr move q and add q. So this instruction updates the value of RAX, and this one actually uses the value of RAX. So surely there's dependence between the two, right? But the difference from the previous example is this one is actually a load instruction, mr move q. So mr move q means you actually read the value from memory, not from ALU, right? So, so in this situation, let's think about this case. In this pipeline, when the value of this like mr move q, the load instruction, when the value of load instruction becomes available, when this one becomes available, in what cycle? 사이클 몇 번에서 값이 실제로 가용하게 되죠? 이 로드 명령어의 결과는 8, 그죠? End of cycle 8, right? Because you actually have to access the memory in order to get the value, right? So in this case, the value becomes available somewhere around here in cycle 8, probably near the end of the cycle 8, because you need to access this memory, like this data memory in cycle 8, right? So your value becomes available here. But when this value is not needed, so in order to forward the value to the pipeline register, we need the value here, right? So there's mismatch, because this value, this register value is needed by add instruction in D stage, but this value becomes available only at the end of cycle 8. So there's mismatch, right? So you can only pass this value back in time. It's like a time travel, right? You actually send the value back in time. It's not possible, right? So in other words, there's like you need to, in this case, you cannot really avoid stall. You still need to stall for one cycle. Then if you actually stall for one cycle, then you can actually send forward the value to the D stage for the next like instruction. So this is called like a load use dependency in general. So if like there's a load instruction followed by immediately followed by like a use instruction, like a consumer instruction, then there will be some problem. You need to still store for one cycle. So value needed by the end of decode stage in cycle 7, but the value read from memory in memory stage of cycle 8. So there's a one cycle discrepancy between the two. So in this case, though, the only solution is you still need to stall. So let's say if you stall it, then now the value becomes available here, and it will be forwarded to D stage here, like this. So now we can complete the D, like a forwarding within the within like a D stage, like this decode stage. So if you stall using instruction for one cycle, then D stage can pick up the value by the forwarding from the memory stage. That's called load use hazard in general. Okay? 그러니까 로드 유즈 해저드가 발생하면은 한 사이클 포워딩을 하더라도 한 사이클 쉬어야 돼요. 한 사이클 스톨 해야 돼요. So you can only avoid stall if you actually have load use hazard. And so how we can detect this load use hazard? So let's think about it. So if you want to detect like a load use hazard, then the instruction in like E stage is either load. This is load, right? MR move, either load or pop Q. Pop actually load use hazard can happen for pop instruction too, because the value is available in mem stage for pop instruction, right? Because you need to access the stack. So if the instruction is either the preceding, like a producer instruction is either load or pop, and the destination register is matches in one of the following like source registers, then we now find this is load use hazard. Okay. And if you detect a load use hazard, what you need to do, how we need to control this hazard. So if your load use hazard happens, then we need to stall for one cycle, right? So stalling means, in this, let's say this one is load, this is when we actually have like a load use hazard. So in this case, load instruction is in E stage, and the use instruction is in D stage, right? So if this condition is detected, then we need to stall for one cycle. And whenever we stall it, we actually, stall these two, like, two instructions in F and D stage, and these two instructions make a progress, and we actually insert bubble in between. That's a stall, right? So that's what happens here in cycle 8. These two instructions actually move forward to W and M stage, and these two instructions actually stays there, D and F stage, and we actually have one like an empty like a slot available in E stage. Now this one becomes bubble like this. Okay, the stall happens in this case. All right. So any questions about forwarding techniques? Okay. All right. So let's move on to control hazard. So if you remember the big picture I draw here, now we covered this thing, Now we're moving to branch prediction, and this time in this lecture and the next lecture. So that's what we're going to cover. So here is a branch prediction example. So here, let's think about this branch case. So here's the XOR Q. What's the result of this value, RAX here? 0, right? If you XOR the same register, then value will be always 0, right? By the way, the answer for, I don't know how many of you actually get the question right. The question we asked, one of the questions we asked was swap the value without using temporary storage or memory. That's using like XOR. XOR 3 times, then you're done. Yeah. So XOR is a very useful operation, by the way. So in this case, if you actually do XOR RAX, then RAX will become 0, right? And if you execute JNE, jump not equal, then this branch will be not taken, right? Because this branch is taken only if value is non-zero. I mean, not equal, right? But in this case, the value is 0, so we always move to the next instruction, right? That's the correct behavior. So we execute XOR followed by JNE followed by IR move Q here, like a red one. That's the correct behavior of the program. But in our pipeline, if you remember, in our pipeline, we always, whenever there is like a branch instruction, we assume the branch will be taken. That's our assumption, right? So we actually, fetch. We take the next PC from the target address from JNE. So in this case, this is target, and this instruction should not be executed, but we need to only execute. The correct behavior is we only execute like this block of code, but not any of these. That's the correct behavior. But let's think about how this instruction will be executed in the pipeline. So here, if you execute this code, the first instruction will be XOR. The second instruction will be JNE, right? And in the pipeline, we get to know whether this condition is satisfied or not only in E stage, like execute stage, right? So until we get there, we make the assumption that, it's likely to be taken, so that we actually take instruction from the target address of jump. That's pipeline design. So once you pass this JNE instruction, now the next instruction is fetched from this a target here, this thing. This instruction will be read from in cycle 3. So in cycle 3, we read one instruction from the target. And cycle 4, we read the second instruction from the target, right? And then later, when this instruction finally get to E stage, when this instruction gets to the E stage, now this instruction knows that I fetched the wrong instructions, right? Because I'm supposed to fetch the instruction from the follow through the next instruction, but not from the target. But it only finds that information in E stage. Now it actually corrects the behavior of the pipeline. So the correcting means, so in the next cycle, it actually moved to the next stage, and these two instructions now turned into bubble, turned into knob. Okay, now eventually they are now turned into bubble or knob in the pipeline in E and D stage. And now, in the following cycle, we now fetch the correct instruction from the fall through path. Okay. So in general, in our pipeline design, we predict branch as taken. So if you fetch two instructions at target, and we cancel them if it's mispredicted. So we can actually detect whether branch is taken or not in the execute stage. On the following cycle, we replace those instructions in execute and decode stage by bubbles if it's mispredicted. I mean, this correct prediction was wrong. And fortunately, no side effects have occurred yet. So it's okay to just flush these two instructions, and we are still correct. I mean, there's no problem in the param correctness. So that's basically how we handle this branch misprediction. So here is how we detect a branch misprediction. So here in EX stage, let's say the current instruction in execute stage is branch, and the C and D, the condition is not true, then we conclude that there's a misprediction happened. If this condition is satisfied in E stage. So now we know that there's a misprediction. Then we need to take an action to correct this behavior. So here, if misprediction is detected, so this at this cycle, misprediction detected. If it's detected, then now we can insert, basically turn these two instructions into bubbles. So, and then we actually fetch from the correct PC, correct destination of the branch. So if this situation happens, then in the next cycle, we replace these two instructions in D and E stage with the bubbles, and these two instructions actually move forward, and this we actually fetch the correct instruction from in the fetch stage. Okay, so it'll be like this one. Like this one like this one like this. this one like this, and this one like this, like that. Okay, so whenever there's misprediction, we actually have to replace those two instructions from fetched from target, replace those instructions with bubbles, and then in the fetch stage, we get the correct instruction. And the next example is return. So how we can handle return instruction. So in case of return, we actually need to, our basic policy, the baseline policy was whenever you have return instruction, we simply, stop fetching the instruction until we reach the write back stage. That's our baseline policy. So here, let's say we have call instruction, and here's the return. So whenever we actually hit upon return instruction, we stop fetching instruction, basically placing NOPs, no operations, until this instruction reaches this write back stage, and then only after that we actually fetch the correct instruction. So let's say we have return here, so we fetch the return instruction here. Then the next three instructions will be basically NOP. We stop fetching instructions, stay there. We'll stop fetching this instruction for 3 cycles, and when this one actually reaches a W, write back stage, at that point now we can get the correct return address, and then use that address to fetch the new, fetch the correct, get the correct PC address for correct return address. So generally, as return instruction pass through pipeline stage, stall at fetch stage. Basically, if you actually have a return instruction, the return instruction move through the pipeline, but the next instruction is basically become NOP. Okay, it basically just nothing. So and then we inject bubble into decode stage, and we release the stall when that instruction reach the write back stage. That's how we handle this return instruction. So how we can detect return? So return instruction, if the return instruction is either in D stage or E stage or M stage, then we don't do fetching. I mean, we stop fetching, basically free stall the fetch stage, and then insert bubble into the decode stage, and so on. That's actually done. Actually, you know what? So the time is up, so I'm going to stop here, and then I'm going to cover this return instruction again, next time, and then move on to next topic.